All right, we've been discussing the idea of a weighted piston cylinder. Again, a piston cylinder is a generic system where the volume can change. That's not the only type of system where the volume can change, but that's the most common one that you'll encounter. It's a very simple way of diagramming it. But anytime you have volume changing in a system, anytime I've got volume changing in a system, something causes that volume to change. That means that we must compute the amount of work done to cause that volume to change. Right? How do we do that? Well, remember, again, we're talking here about work. Work must be done. How do we find work? Well, again, work is the net result of a force applied over a distance. I've got this thing sitting on my desk and I've been debating on it's like a hot dog, but I've worn most of the paint off. It's a stress reliever, right? And so you can see that this is a thing it's a stress ball, and I can change the volume of this thing by applying force to it. As I apply force, I get resistance from the sand inside this thing or whatever the substance inside this thing is. So that's the kind of idea is that if I apply an external force and I cause the volume of my system to change, that means I'm actually applying a force over a distance. And the same thing is true if the system is expanding. If the system is expanding, right, if I've got a system and it's expanding out into the surroundings, it has to push those surroundings out of the way. It has to apply a force. What generates that force? What generates that force is pressure. Remember, pressure is force per unit area, which means that force is pressure times area. Force is pressure times area. So if I need to compute the work required in order for the volume of a system to change, that means there's internal pressure applied over an area causing the force that's being applied over some distance. And I need to integrate, find the net result of that pressure applied over an area through that distance. Now, a neat little dimensional analysis trick here says that if I take this area and I multiply by a differentially small distance. Well, and here I would ask my class, okay, what happens when I multiply an area times a distance? What do I get? And I'll wait patiently until somebody tells me volume, right? If I take area times distance, that gives me then, that gives me then a volume. So what happens if I take an area and I multiply? So here I've got an area. What happens if I take this area and I multiply it by a tiny little differential slice of distance? Well, I'm still going to get a volume. This work is equal to the integral of pressure. And if I take area times distance, that's going to give me a volume, even though it's a differentially small volume. Pressure integrated over volume gives me work. And what we find is that if the boundary is moving, if we compute work in the out direction, that means I'm integrating from the initial volume to the final volume, pressure with respect to volume. Boundary work in the out direction is equal to the integral from initial to final volume, pressure with respect to volume. So notice on this diagram here that if I start at some initial volume and I go to some final volume, in this case, I'm expanding. I'm expanding. That means the system is pushing the surroundings out of its way to get from state one to state two. Notice this is path dependent, right? If I've got, let's do a different color here, right? If I've got maybe some kind of a green, if I've got a path that goes up here and comes down, notice that the work done, it now must include this area up here. That's a different area than what you see from here to here. And if I had a straight line, that's even a little bit different work, not a whole lot different than the red area you see here. right? But again, the area bound by a curve represents the integral. If I integrate pressure with respect to volume, that represents the amount of work done to get from point 1 to point 2, and that quantity is path dependent. If I put another color in here, if I went like this, that's a different amount of work, right? So how I get from 1 to 2 is important. So what that means is I need to know how the pressure changes as volume changes in order to figure out how much work is required for this process to occur. Okay. Now, why the direction? And I've got these two GIF images that are somewhat out of sync, but hopefully you get the idea. If notice what happens when this system expands. When it expands, it compresses the spring. So here it expands, it's compressing the spring. When it's being compressed, the spring is expanding into the system. So notice where the energy is. Right now, the energy is here. Now the energy is up here. Now the energy is here. Now the energy is here. When the system expands into the spring, the energy gets stored into the spring, meaning that the system, when it's expanding, when the system is expanding, that means there's work going out of the system. When the system expands into the spring, the energy gets stored into the spring. And when then but the opposite is also true. If the spring pushes into the system, that means energy is going from the spring into the system. So expansion is work out, compression is work in. Okay, and that's really important. I want to actually let's write that down. That's really boundary work out is equal to the integral from initial to final volume pressure with respect to volume. I'm not kidding when I tell you, literally, our entire society is built off of this principle. This is very important. If V2 is greater than V1, this is what we call expansion. My system is going from a smaller volume to a larger volume. That is expansion. The system is expanding into the surroundings. For that to occur, the system has to push some of the surroundings out of its way to expand into the surroundings. The system is doing work to the surroundings. Boundary work is going out. You have positive boundary work in the out direction. On the other hand, if I'm going from a larger volume to a smaller volume, if I'm compressing the system, this is what we call compression. If the system undergoes compression, that means the surroundings have had to put work into the system. If I compute the amount of work in the out direction, if compression has occurred, I will get a negative work out, which is the opposite of work out, which is work in. I'm basically computing the work in for the compression to occur. So expansion means work out. Compression means negative work out. Work in if you like, because then what happens? Well, when I plug it into my first law equation, if I plug in negative work out, that gets added to this side of the equation the same as work in would. So if I compute negative boundary work out, I can either plug it in as a negative work out term, or I can plug it in as a positive work in term when I plug it into the first law. As long as you're careful about your signs, either one of those is technically correct. I'm out of habit going to plug it in as a negative work out term and let the science take care of itself in the first law. And that's one less thing I have to remember because I've got way too many other things going on and I get distracted easily. Very, very important concept. Worthwhile we took a minute and really hammered that down. Hence the reason I've drawn this ridiculous GIF, well, two GIF images, found one and created the other, and I'm sad to say they're just not synced up. But hopefully that gets the idea that when the system's being compressed, energy is going from the spring into the system. And when the system's expanding, it's pushing energy from the system out into the spring. Hopefully that helps. Okay. Now, as we mentioned back here, we said, hey, I need to know how I'm getting from point 1 to point 2 to perform this integral. I need to know how pressure changes as volume changes. Is it up here? Is it down here? Is it straight across? Those are three different works because it's three different process paths. So what does that look like? Well, there are three main types of pressures as a function of volume that we're going to encounter in this course. Now, that doesn't mean those are the only ones. In fact, there's four we can talk about here. The simplest one that you'll encounter a good amount is the constant pressure. Constant pressure is the easiest integral. We'll see that pretty quickly. In fact, the first example problem we work will have a constant pressure. Ideal gas law is a way of relating pressure to volume, especially if you know how the temperature relates to pressure or volume, and you can simplify that expression. If it's isothermal, then that gives you an expression you can work with. A very common one, though, that we'll use. We won't use the ideal gas very often, but the most common one that we'll use is either constant pressure, the polytropic process, where P times V to some power n is equal to C, where both n and C are constant values. And that means then that means P, if I solve for P so I can plug up my integral, that is C over V to the n or C V to the minus n. Either of those are just fine. They're the same thing. The last one we might encounter is a linear expression where I've got basically P is equal to mx plus b, or y is equal to mx plus b, if you will. It's a nice linear equation. This basically becomes P is equal to some constant, we'll call it m just for familiarity, times my dependent variable, that's v, plus some other constant, basically the y-intercept, or the P, the initial pressure, if you will. P is equal to mv plus b. Sometimes it'll be AV plus b, but I use m and b because you're familiar with that for a linear equation. It's just instead of x and y, we're using pressure and volume. If I've got a spring attached to that piston cylinder, springs will often apply essentially a linearly varying force, meaning the pressure is going to ramp up in a linear fashion or relax in a linear fashion as the volume changes, because you've got a linearly varying force applying that pressure spread out over the area, the top of the cylinder. So you'll encounter sometimes spring-loaded pistons in the homework sets where you may have to generate this equation, this pressure linear equation, and then run it through this integral. And that's an easy integral, right? The easiest integral is the constant pressure. Polytropic is not a hard integral. That's basically a polynomial. Or the linear, which is basically a first order polynomial. So all those are very simple integrals to do. I need you to be able to do basic integrals, but we're not going to, you notice here, there's really not even any substitution. Never trig substitution. Yuck. Anyway, let's keep moving. What else then? Oh, example, which is not a bad place to stop and pick up the next video. So that's what we're going to do. We're going to stop here and we're going to solve this in the next video on its own. Okay. Stop recording.